Hey, hi guys, good morning.
Good morning, sir.
So today we'll discuss about multiple linear regression. But before we get into this topic, any questions on simple linear regression? Okay. All right. Let's talk about multiple linear regression. Um, Multiple linear regression, as we discussed, here we will consider multiple input variables. Earlier in simple linear regression, we have considered only one single input variable, but here in multiple linear regression, we can add more number of input variables. So here in the same example, now we are going to consider three features now. Engine size, along with engine size, we will also include cylinders and fuel consumption. So now we will have three independent variables and one dependent variables, and we will build a model like this where we will have uh, four coefficients, one intercept and other coefficients for each of those variables. Okay, so here again, the cost function would be this mean squared error. Remaining everything would, again, here the gradient descent will try to reduce this MSE by optimizing the parameters, which is nothing but the coefficients, and will try to find out the best coefficients, which will give you the uh, best fit line, right? And now based on that particular model, now we can able to predict the CO2 emission with the help of these three features. Again, this method is also method is called as ordinary least squared. Okay, so where um, the whole objective would be to reduce this squared errors. Okay, that is known as ordinary least square. And here we will use this optimization algorithm known as gradient descent. Okay, and now why, as I mentioned, instead there is one statistical approach as well. Okay, so where it will do some kind of matrix multiplication and calculation, and it will try to find out the best optimal values for those coefficients. But generally, it takes a long time for large data sets, and it uses some linear algebra matrix calculations to estimate these coefficients. So yesterday we have seen both the methods. The first sklearn method is based on this optimization algorithm. The another one, the statsmodel.api package where we have used, there it is using the OLS method. So it is a traditional statistics based method. But as I mentioned, it doesn't work well, when we have a large data sets. Okay, for example, more than 10K plus rows. So there, it takes a lot of time to you know to find out those optimal values. However, with the help of this gradient descent, we can scale it to a larger data set. Even if we have more number of variables or more number of observations, this particular algorithm can very easily can find out the optimal values of theta or coefficients. So in the multiple linear regression, again, once these coefficients are identified or calculated, we will get the equation like this, where y hat is your predicted output variable, and the equation would be something like this. And based on this, we can able to find out the CO2 emission. And again, we need to have a training data set to train the model. Once the model is trained, then we will go and test that model. And if we find the accuracy is good enough, then we can use that particular model for predictions. Okay, and this is how, basically your gradient descent would look like. So if you see that it has multiple, it is iterating multiple times, right? So at this particular point, the cost is this much. So if you see at every step, it is descending. Okay, it is kind of trying to minimize the cost function, and finally it will converge here. Okay. Um, so if I put it in a 2D format, so it is something like this, right? So it started from here, the cost would be this, then it will descend, 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 descend. Finally, it will converge at this point where the slope is zero. Now that would be your global minima at which it will converge. And at this point, whatever is your coefficient values, or we also call as weights. Okay, and this W is nothing but the weights. These coefficients are also called as weights. So it will converge at the point where the cost is minimum, and that would be your optimal values. At different cost function, if you see here, it will come up with a different line, regression line. And then finally, it will find out the best regression line, which is called as a line of best fit. And that would be your final model. In the 3D plot, it would look like this. Okay, so it's showing in a 3D format because we cannot plot beyond 3 dimensions. But if you have a larger data set, just you have to imagine that this particular optimization algorithm will take n-dimensional space, and in n-dimensional space, it will iterate and it will find out the best optimal values. Okay, so now, as I called as a weights, now how you will read this particular equation? So here, this is also known as the bias term. Okay, we also call as intercept. So this is known as bias. Now, these are known as weights or coefficients, right? How you have to read it with a 1 unit change in x1, there is a 6.2 units change in your output variable. Similarly, here with a 1 unit change in x2, your predicted value would change by 14 units. So with these weights, you can also uh, comment on the significance of each of these variables. See here the weights is 6.2, here the weight for x2 is 14. So with these weights, we can understand that this particular variable x2 has a higher influence on this particular output variable. Because 1 unit of x1 is impacting by 6.2 units on y hat, while 1 unit change in x2 is impacting your output variable by 14 units. So with this equation, you can also understand which of the variable are of higher significance and which variable are of higher importance. Okay. So that's how, you can understand which variable is contributing how much, on the output variable. So this is as simple as that. Now, before we get into the use case, yesterday I've shown you one evaluation matrix as R square. Okay, R square value. So this R square is a statistical measure for measuring the significance of regression model. Okay, and now this would range between 0 to 1. So if it is close to 0, that means the model is not good. If it is close to 1 R square value, then that means the model is highly accurate. The statistical definition of R square is it's a measure of variance captured by the regression model. Now, what is this all about? So let's understand this. Okay, let me draw a scatter plot. So for the ease, let me draw only few points. Okay. And let's suppose this is my regression line. Let me take only one single point to explain this whole concept. So let's suppose this is my yi. Okay, this is my actual, and this is my prediction. So how you will calculate the prediction? So at this particular x value, let's suppose this is my x1, this is my y. At this particular point of x1, this is my yi, which is my actuals. Okay, that you can get it by the from the data, right? So in your data, you have x, you have y. So let's suppose at one particular point xi, this is your yi. So this is your xi, and at this point, this is your yi. The same, now we have an equation also, y hat equal to beta 0 plus, let's suppose, beta 1 x1. Now with this, at this particular xi, I will calculate this y hat. Now this is my, as this is my regression line, so this is my yi hat. Okay. Now we have to, now this R square, what it does is, it will calculate how good your predictions are when compared to your actuals. So how it will calculate? Here comes one more um, base model from which this regression model will be compared. Now that base model is known as null model. Now, for example, now you don't know about statistics, you are not a data scientist, you don't know about machine learning. How typically in our real life we predict things? So, for example, if I ask you, how much is your, what would be your expenditure tomorrow? How would you predict? How would you answer to my question? Anybody? So tomorrow it didn't come, right? So it's a future thing. If I ask you, how much would you spend tomorrow? Roughly, if you have to guess, how would you guess? Anybody?
Based on the weekly average or something, or a monthly average?
Yes, average. So that's your null model. So typically in the real scenario, what we do is we go with an average, and that we have also discussed when we were discussing about mean, median mode, right? So null model is nothing but your y hat. So in your data, whatever values of y are there, okay, you will just take the average of it, and based on that, that would be your prediction. That would be your single prediction. Okay, every time, you will go with this mean only. Let's suppose now that is this particular straight horizontal line is your null model. Now see, now this is your actual. Now this is your null model, which is your mean. And in between, it's a regression line. It's your predictions. Now this is your actuals. With this actual, the difference from the mean would be this much. Okay. So I'll just draw a straight line here. Okay. Now this particular portion is your yi minus yi hat. This is the residuals or errors which is coming out from your regression line, which is the difference between your actuals and the predicted value of the regression line. Now, this particular, the whole from yi till y bar is your difference, or you can call it as an error of your null model. So, for example, now the actual value is 150 and your mean value is 70. So, difference would be 80. 80 is your overall error with your null model. Okay, and let's suppose your prediction is equal to 120. So your residuals, which is the difference between your actual and the predicted values, would be 30. Now, definitely there is an improvement if I'm going with a regression model rather than the null model. But overall, for all the points, how good that model is when compared to the null model is something we are going to measure with this R square. Okay. So how we will do it? So now let's suppose this is my total error. from yi till this y bar. Okay, so what I will do is I'll just write it like this. Y bar is equal to yi minus yi hat plus yi hat minus y bar. Can I write like this? This is my total error. Okay, from yi till y bar is equal to this error, this residual plus this difference, right? So now what I will do is now I will calculate this for all the i's, right? So I will just put a summation I equal to 1 to n, where n is nothing but your sample size, okay, or the data or the training data on which you have trained the model. Now I'll put this summation, so it will find out for all the data points. Now you have seen that in statistics we always take the magnitude, okay, or the quantitative value, okay, or we just scalar value. So what we do for that, we take the square. So we will do the square, okay, on all the sides. Otherwise, if it is plus minus, so it will kind of get subtracted and then it may give you 0. So to avoid that, we will take the square of all these differences. Now, in statistics, the name of this particular term is known as SST, sum of squared of total errors. Okay. Now, this one is known as sum of squared of errors, or sometimes it is called as residuals. Okay. And this is known as SSR. So that means sum of squared of regression line. So basically, now if you see here, if your regression line is better, okay, so now this particular line would be closer to the points. Now this has to be low. If your regression line is a good line, is a line of a good fit, then this particular difference, which is the difference between your actual values and the predicted values, would be less, right? And this would be more. So if this is high, if this is low, then your model is a better model. So so the R square formula is SSR by SST. So we will try to find out what is the proportion of this SSR of this SST. If the proportion is high, for example, out of the total error, now this is covering around 80% of the total error. That means your model is good model because only 20% of the error is left. So that means this is 20%. Now this is 80%. Now overall it is 100%, right? So if this is your overall error coming out from your null model, but your regression line has reduced it to 20%. So that means 80% of the error it has able to capture. It has able to uh, uh, those errors it has able to reduce, from when compared to the null model. So the only 20% error is left now if you're going with a regression model. So earlier where you were predicting by the null model as 70, now with the regression model, I am predicting as 120. So how much error is left now? 30. Earlier where you were making the error of 80, this regression line, now I am making the error of 30. So how much error it has captured or how much variance it has able to capture, that is defined by this SSR. So the ratio of SSR by SST is known as R square value. In some of the books, it is also written as so SSR, you can also write it as SST minus SSE divided by SST, or 1 minus SSE by SST. Okay. So this is known as your R square. Okay. So take a minute. Let me know if you have any questions. Is this clear to all of you? Now this is your R square. So no need of again mugging up this formula. Just you need to understand when somebody is asking you what is R square, then you have to say it is a measure which will tell us how much variance the regression model has captured. So if it has captured more amount of variance, so that much good the model is, right? Now, there is another term which we'll find along with the R square, which is known as adjusted R square. So what is this adjusted R square? Typically, what happens is if you are moving from simple linear regression to multiple linear regression, where you are adding more number of features to your training data set, will see that as you are adding more number of feature, your R square value will increase. Okay. But statistically, do you think that is a good way of improving the accuracy of the model? It's not. In statistics, that you are pushing your model to overfitting. Okay, if you keep on adding the more number of features into your training data set, and if you simply observe the R square, you will end up overfitting the model. And generally, what happens is if you keep on adding more number of variables, R square typically increases. Okay, and you will feel that you are improving the model, but the reality is different. Okay, you are not improving the accuracy of the model, but you are overfitting the model. So in that case, rather than R square, we will go and look at adjusted R square. So we have to simultaneously, we have to observe the R square and adjusted R square for multiple linear regression. For simple linear regression, we do not have any such problem, right? Because we are going with only one single variable. In multiple linear regression, one by one, we keep on adding the variables to see that how it is improving the model. And for that, instead of looking at R square, we look at adjusted R square. Now, what is this adjusted R square? The formula of adjusted R square is 1 minus R square into n minus 1 divided by n minus k minus 1, where n is nothing but your sample size, your training data, and the size of your training data, and k is equal to number of features. So what it does is adjusted R square. If your feature is not significant, if it is not important, okay, if it is not influencing your output variable a lot, if you add those kind of variables, your adjusted R square will go down. So as in multiple linear regression, if we are adding a variable one by one, and if you come across with a variable which is not significant, your adjusted R square value will go down. However, your R square value may increase, but your adjusted R square will come down. So there you have to stop. There you have to um, you should not consider that particular variable which is impacting your adjusted R square. So for multiple linear regression, again from the interview perspective, you may get the question like in multiple linear regression, would we consider R square or adjusted R square? So your answer would be this. And if somebody asks you why adjusted R square, then you have to say that this measure will penalize uh, penalize if we are adding a non-significant variable into our data set. Okay, so now this is the formula for adjusted R square. Okay, so this is about R square and adjusted R square. Now let's get into a use case. Okay, Harishri is asking, could you please repeat SST full form? Okay, so it is sum of squared of total errors. So total error is this, actual minus your mean. Actual minus mean is known as SST. So basically, I will calculate for all the data points. like y1 minus y bar, y2 minus y bar, y3 minus y bar. For all the data points, I will find out the difference. I'll take the square and then I will sum it up. And that will become my sum of square of total error coming out from my null model. So that is your SST. Now this is your sum of squared of residuals. Residuals we discussed, right? Residuals is nothing but the difference between your actual and the predicted value coming out from your regression model. So now that is defined as SSE. Okay. Now this is sum of squared of difference between your regression model output and your null model output. So they have named it as SSR. Okay, so in different books, you will find different notations. So the book which I have referred, in that book, it is referred as SST, SSE, and SSR. Okay. Now, to find out how good your model is, you have to understand what is the ratio of this particular component or this particular uh, part of your total error and compared to the total error. So that is nothing but your SSR divided by SST. If it is high, so that means this component is less and this component is more. So what is this component? This is the variance captured by the model. Where you are going with just a null model. Now with the help of this regression model, you are able to make much more better predictions. Okay, that's what this R square signifies. Okay, so any other questions? Is it clear to all of you? All right, so now let's get into the use case. Yesterday, we have looked into this particular data set. The same data set we will see. Anybody remembers how much R square we have got yesterday with the simple linear regression, where we have considered only one single variable? Anybody remembers the R square value?
0.7.
0.7, right? So with the one single variable, which was engine size, we were getting R square as 0.7 something, right? So that means the 70%, the model was 70% accurate. It could able to reduce the error by 70% when compared to the null model. Now let's see, how we can improve. Yesterday I mentioned, right? If your model is not good, okay, so you have to upgrade your algorithm. So if the simple linear regression is not giving you a better result, upgrade to multiple linear regression. If even the multiple linear regression is not giving a better results, then you go with other complex algorithms in machine learning, which we will discuss. You can go with decision tree, you can go with support vector machines, so and so forth. So here now we will go with this multiple linear regression, and if we are going with multiple linear regression, we have to add more number of variables. So again, the process would be the same. Okay, you have to go and analyze the data. Okay, you have to look at the data. You have to understand which of the variables could be important. That comes by domain knowledge, that will come by some kind of research, or even that you can do it by doing some kind of correlation analysis, right? In the correlation analysis, you will see that which of the variables are highly correlated to each other. So there you have to find out the correlation of these input features with the output variable. Okay, so you can refer to yesterday's code where we have developed that correlation matrix, right? And that correlation matrix is helping us to understand how each of the input variables are related to the output variable. Now, with that particular correlation analysis, let's for this particular data set, let's assume that these three variables are strongly correlated with this CO2 emission. Okay, it was somewhere 0.86, 0.89, right? So these three variables have been chosen as the most important variables, which are highly correlated with your output variable. Now, earlier where I just considered only one single variable, engine size, now I'm considering these three variables. So now it becomes a multiple linear regression problem now. The method is almost the same. The only difference is here in the x um, um, in the x, where where we have considered only one single variable. Now we are considering three variables. That's the only difference. Remaining all the steps are same. Okay. So if you see that the model training is happening with these 3 or 4 lines of code, that's all. Okay. So it is as easy as this, right? So you will see that every machine learning algorithm which we are going to discuss with a single line of code, you can train the entire model. Before that, but what you have to do is you have to do the split, you have to do some kind of pre-processing. That would take a lot of time. So if you remember my earlier classes where I discussed about that CRISP DM, which is your ML project life cycle, data preparation takes more than 70% of your time. Model training will not take more time. Just with one single line, you can train the model. So nothing much you have to do. Later, we will see there would be a little bit of parameter fine tuning, which you may have to do, okay, to improve the model accuracy. But that is not that would not take significant time. But significant time will be taken by this for this data preparation. So we'll discuss more about data preparation. But for now, here we are considering three different variables, input variables. That's the only difference. Remaining everything is the same. Again, I'm considering this linear model from sklearn, and I'm initializing this particular algorithm, linear regression, and then I'm fitting it on this input variable and the output variable. Always make sure that the length of this input variable and the output variable is the same, and it should not you should not shuffle. Okay, sometimes it happens like if you are doing too much of pre-processing, and as these are two different objects, the order of the observations may change. Okay, so you have to make sure that otherwise what will happen is the first row of x is different, the first row of y is different. So if you are feeding that kind of a data to the model will try to identify the relationship between that x and that y, because that will not understand if whether the data is shuffled or it is aligned, right? So you have to always make sure whatever data x and y, whatever you are passing to this particular model, is of exact length and they are aligned. So the first observation of the x should represent the first observation of y, right? So that's how you have to prepare your data. Now go and pass this x and y to this particular algorithm, which is linear regression. And just within fraction of seconds, it will give you the coefficients. Now these are the coefficients. So if you say this model dot coefficient underscore, it will give you the coefficient for each of the variables. Now how you will read this, as I just explained. So here the first 1 unit of change in engine size is influencing your output variable by 9.9 units, right? And this by 7.5 and this point 10.1. So the higher weightage is given to this particular variable, which is your fuel consumption. Okay. So if somebody asks you which of the variables are of high, which variable is of high importance, then you can say that fuel consumption, followed with engine size and followed with cylinder. And if you observe the correlation, there also you will find that the correlation would be higher for fuel consumption, then engine size, and then cylinder. Okay. Now this is your intercept, so also called as the bias term. So your equation could be with this also, right? Your output variable CO2 emission is equal to 9.9 of engine size plus 7.5 of this cylinder plus 10.5, 10.1 times of fuel consumption. But what is this? This is the intercept, which will get added to the equation as a constant, right? 61.8. Now, this is known as bias because now this is the line equation, okay, which will give you the line, straight line. But this intercept will elevate the straight line. How much above the zero axis, how much below the zero axis is something, which you can understand through this intercept. And that's how, the the regression line will get adjusted. So there's a reason it is also called as bias. So bias term gets added to the equation to um, to balance or to optimize the model. Okay, and please remember this point. This point we will again discuss in the neural networks. Okay, and there the bias term will play a very important role. Okay, so this is your entire model now. Now, once your model is you identify these coefficients and intercept. Now with this you can do the prediction. Now let's so here I've given some literature on the OLS. Okay, you can go through it. Now, if you want to do the predictions, so here this is your model which has been trained on your data set, and this model consists of all the coefficients and the intercept. Now use this particular model, say dot predict. That's all. So predict is the function in sklearn which we have to use for predictions. You will just pass the input variables. So from the test data set, I am passing these input variables. Okay. Now this will give me the y hat, all my predictions. Okay, so this is not required. Okay. Yeah, this is we are doing it for test. Earlier we have done it for train, right? So now these are my predictions, and these predictions I will compare with my actuals, which is y, right? So here what I'm doing, I'm finding out sum of square, mean sum of square, MSC. Okay, so this is my MSC, mean squared error, which is 498. So if you want to, now this is at a higher scale, we are squaring the errors. Now to bring that to the same scale, what you have to do is you have to take the square root. Now that will become your RMSC. Okay, so just take the square root of this term, it will give you the RMSC score. Now this is your R square. Okay, so if you just say REGR, this is your model, and say dot score and pass this X and Y, it will give you the R square score, or else you can also find out the R square score through with this particular function also. It will also give you the same score, 0.87. Okay, so there are multiple methods in Python, guys. One single task can be done in multiple ways. There are multiple packages, there are multiple functions. So do not get confused. So here, this is one of the method of calculating the R square. This is the another function, for calculating the R square. Eventually, you will get the same score. Okay, same value. So it's up to you which one method you will follow. Okay. So this is the same set of code which we have used yesterday. So now if you see earlier when we are doing with a simple linear regression where we have considered only one single variable, there we were getting the R squared score as 0.76, right? Or 73, whatever. Now here we have improved it to till 0.87. So now the accuracy is 87%. If you keep on adding more number of variables, important variables, then probably you can also able to reach to 90% or 95%. So that kind of iteration you have to keep on doing till you achieve the better accuracy. Okay. Now let's do it with this traditional method, statistical method. Okay. So when we use this statistical method, we will get a lot of information about the models, which is called as statistical summary of that model. So here, if you see, we have R square and we have adjusted R square. So when we are dealing with a multiple linear regression and we have to compare whether by adding a variable, whether it is improving the model accuracy or not, there you have to refer to this adjusted R square. Okay, there would be slight difference. This R square will keep on increasing as you add more number of variables. But this adjusted R square will not improve until and unless that particular variable is important, until and unless that variable is statistically significant, right? If you have added, let's suppose, one single variable, But if there is no improvement in the adjusted R square, sometimes it may also go down. Okay. So that means that particular variable should not be considered, okay, for your model training. So in that way, you can select the appropriate and the best variables which can improve your overall model accuracy. Okay. Now, coming to this we have discussed yesterday also. So these are all my input variables along with the intercept. Intercept is here, it is called as constant. This is a constant term, 65.95, or called as bias term. And these are the coefficients for each of these variables. I'm not sure if these coefficients are the same what we have got here. 9.9, 7.5, 10.1. So there would be a little difference, right? There's a little difference. So as these two are two different methods, we will find slight difference in the coefficient values. Okay, so now here on every coefficient, whether it is intercept or whether those are coefficients of each of these input variables, it is undergoing the t-test. What this t-test does is it will test whether that particular variable is statistically significant or not. One way is like through adjusted R square, you can identify whether that is significant or not. Or else you add all the variables at once and then look at their p-value through this t-test. Wherever the p-value is lesser than 0.05, there you can reject the null hypothesis, which says that that particular variable is not significant. It is kind of equal to 0. The coefficient is almost, you can consider as equal to 0. So that means that particular variable is not significant. So if the p-value is less than 0.05, then you can reject your null hypothesis. By now, I think you remember that particular thing, right? We have done so many hypothesis testing. If the p-value is less than alpha, and in the industry standard, if the alpha is not given, then we will consider as 0.05, which is 5%. If your p-value is less than 0.05, then you can reject your null hypothesis and you can go with the alternate hypothesis, which states that that particular variable is significant. Here, my all p-values are less than 0.05. So that means all my coefficients are significant. So that means in the equation, all the coefficients are important to consider and all the variables are important to consider. Let's suppose in one of the cases, for one of the variables, if your p-value is greater than 0.05, then that means that particular variable is not statistically significant, okay, in your model, and you should go and drop that particular variable. You should not consider. So we will talk about variable selection. So this is one of the method for variable selection. So first method we have seen, where we are doing a correlation analysis. We are calculating the correlation coefficient and we are identifying the strength of the relationship, right? Wherever the correlation coefficients were higher, so that means that particular variable is strongly correlated. So that's how we are selecting the variables. That is one way. Second method is this, where we will look at the p-value. And wherever the p-value is significant, so that means those variables are important, and based on that, we will select the variables. The third thing is like by stepwise regression. What is stepwise regression? In every step, I'll keep on adding the variables and I will go and check this adjusted R square. If the adjusted R square is improving, so that means that particular variable is significant. Otherwise, I will not consider. So by now we talked about three different methods through which we can select the variables. One is your correlation, second is your p-value, and third is based on adjusted R square. So note it down somewhere. And further as we go, there are multiple other methods also. And now variable selection is a very important step in overall machine learning model development. And this could be one of your interview questions. How you select the variables, important variables. And if you don't select the right variables, either your model will overfit or your model will underfit. Okay, in both the ways, your model would not be that accurate, which you can push it to production. Okay. So here there are so many non-parametric tests also available in statistics. Non-parametric, so whatever hypothesis testing, t-test, z-test, and all those tests we have done, those are all called as parametric test. So what do you mean by parametric test is in the parametric tests we make certain assumptions. Okay, so if you remember, we always used to make assumption that the population is having a normal distribution, right? And we assume that the variances are equal. All that kind of assumptions we have made for different kinds of hypothesis testing. There are another different set of hypothesis testing which we call as non-parametric. Here we need not to take any assumption. So for example, this Shapiro. The Shapiro test, what it does is it will go and find out whether a data which we are passing it to this particular test is following a normal distribution or not. Okay, so if the p-value is less than 0.05, so that means your model is your data is following a normal distribution. Okay, so as I mentioned, in this linear regression we make certain assumption. First assumption we make is uh, that the input variables and the output variables are linearly related, because these are linear regression models, right? So it will only identify the linear relationship between the input and the output. So that's the first assumption we make, and then only we go and perform this particular model building. We consider this particular algorithm. Second, to consider whether my model is good or not, I have to assume that the residuals, which is nothing but the error, which is coming out from this particular model, are following the normal distribution. And yesterday we discussed, right, why we do that. If it is a normal distribution, that means my errors are equally distributed on the left hand side and equally distributed on the right hand side. So that means your model is not biased. It is not influenced by certain data points. I'll show you this particular graph. Okay. In this particular graph, if my line, one second. So if my line is passing from the center like this, so I will have kind of equal, the errors would be equally distributed on the top and equally distributed on the bottom, right? So in that way, my line is, I can consider the line is passing from the center, okay, from the middle. In that way, my regression line is considered as a good line. But what if, if my line passes like this? Do you think this is a good line? Obviously not, right? Because here all the errors are positive. In that case, my residuals would not be normally distributed. So in that case, let me remove this. So in that case, this tail would be longer on the right hand side, and it would be a very short tail on the left hand side. So with this test, I can understand whether my model is a good model or not. Okay, but why it may happen? Okay, why? Because see, I'm using gradient descent and all those things, and why? How come I can get that kind of line? You can get that kind of a line if there are some kind of outliers existing in your data. For example, now let's suppose there are certain points here, okay, on the top. Only 3 or 4 points are there on the top. For example, if the emission would be around 1,000 or 1,500, so you have few points there. So what it will do is, because see, this regression line will try to reduce the error of overall data set. So if there are certain outliers, it will consider those points also. And because of that, what will happen is, again, I will annotate. So for example, my points are like this here. So here, instead of this particular line, it will go for this line. Okay. Now this would be your regression line because of these points. Okay. Now this line will shift from here to here because in the overall data set, it will try to reduce the error, right? So these are also the points. And so it will consider these points also. So now because of this, now most of my errors would be negative in this case, right? In this case, my residuals would not follow a normal distribution because it will have a longer tail on the left-hand side. Now, this is the indication that your model is not a good model and it is getting influenced by certain data points. Now, you have to go and recheck the data and identify if there are any kind of outliers. So, what are these outliers? So, they are some statistical methods through which you can identify these outliers. But the simplest way is like that you go and find out in this particular column, emission. Okay, are there any such data points which are extremely kind of different, okay, from rest of the observations? So what is the technique through which you can do? You can go and uh, use box plot, okay, which we have discussed, right? In the box plot, it will clearly shows you if there are any outliers or not. And if you find those outliers, just remove those from your data set and then train the model. And then you will get the best line. Okay. And in this, if you get this particular line, of course, your errors or the residuals will follow a normal distribution. Okay. So whether your whether your errors is following a normal distribution or not, second, right. Whether your residuals are following a normal distribution or not, you can apply this Shapiro test on the residuals. Okay. This Shapiro test, if you apply, what I have done is I'll just calculated the residuals. So if you see here somewhere we have calculated the residuals. Yeah, here is the residuals. Predicted minus actuals, or it could be actuals minus predicted. Okay, whatever way you have to calculate, just calculate the difference between these two terms. So that would be your residuals, and that residuals you pass it to this particular function known as Shapiro. Now this will test whether whether those residuals are following a normal distribution or not. If your p-value is less than 0.05, then you can conclude that this residuals are following a normal distribution. Other than this, you can also go and visualize it. Okay. So this is how I'm visualizing. See that how perfectly normal distribution, it is. Okay. It's following a perfect normal distribution. So with this also, you can confirm that your residuals are following the normal distribution. So this is the check which you have to make. There is no one standard matrix which will qualify whether your model is good or bad, right? You have to look, you have to look into from multiple directions. One is like through residuals, you find it out whether your model is good or bad. You go and check the R square, you go and check the RMSE, you go and check the adjusted R square. So all these are important. There are multiple other metrics also, but I will not confuse you. So for now, R square, adjusted R square, and this residuals check is important to confirm whether your model is a good model or not. Okay. I'll take a pause. Let me know any questions. Out of all the machine learning algorithm, this linear regression, in terms of understanding, it is difficult, it is complicated, but in terms of explanation, or like in terms of what do you say, training part, this linear regression is considered as the simpler algorithm. It is the most simplest algorithm in all the machine learning algorithm family. Why? Because it is a very straightforward, and you can see now with this coefficient, you can explain the model. You know, like what is that model? It is a simple equation. The way it has learned, that is also very simple. Okay, so it is changing these beta coefficients and finally arriving at a point where it is getting the minimum cost function. And if you understand the statistical approach, that is also very simple. Okay, through some linear algebra and matrix calculation, it is identifying or calculating these coefficients. But when compared to other machine learning algorithms, no, this approach is quite simple and easy to explain. Okay, but when we get into like support vector machine neural networks, now you'll find in terms of understanding, it could be simple because at a high level, we need to understand those algorithms. So it could be simple, but the way it is training, the way the model is building, that is more complicated when compared to regression. And once the model is trained, it would be hard to explain to somebody. Okay, so you cannot able to explain the neural networks. It will give you the uh, accurate results. It will give you the better predictions, but you won't be able to explain it to somebody. So the model interpretability and the model explainability will reduce as we move from linear regression till neural networks. Okay, so we'll talk about that particular trade-off, bias versus variance trade-off, and that trade-off we have to keep it in mind while selecting the model. Okay. So this is linear regression, guys. This is comes more under statistical modeling because you have seen that we are we are referring to t-test. There is f statistics. There is normal distribution. All those things. It's more of a statistical based algorithm. Okay. But as we move to other algorithms, you will see that those are more of a mathematics based algorithm, less of statistics. Okay. But the main advantage of this linear regression is that if your business is coming and asking you, okay, I need a predictive model, but I need to even understand how that predictive model is predicting the outcome. If that's the ask, then you have to go with this regression model, because with this regression model, you can able to explain. You can say that, hey, this is the model. With this model, you can predict the CO2 emission. Here we have considered these three variables, and the way they are related to the CO2 emission is with this equation, right? And with that equation, you can also help them understand which variables um, are of higher weightage. Okay, so here you can say fuel consumption is having a higher weightage when compared to other variables, followed with engine size and cylinders. So this much clear explanation you can provide to your stakeholders. Okay, with the help of this linear regression. But if you get a customer saying that, okay, with this linear regression, I'm getting only 86%, but I want 95%. Then you can say that, okay, if you need 95%, I have to go and try some complicated models, machine learning algorithms. Okay. And, but the only disadvantage is, yes, you may get 95% accuracy, but the only disadvantage is that you won't be able to, interpret the model, which variable is of higher significance, how they are related. That's something, can't be explained. So mostly those models would be a black box models. We call it as black box methods. Okay. Under that box, inside that box, how the model is getting trained, you will understand at a high level. But what exactly is the relationship if you are passing any kind of a data observation to that particular model? What is happening inside and how it is predicting the result? That something is not clearly straightforward, and you cannot able to explain it the way you are able to explain this regression models. Okay, So that's the trade-off these business have to make. Okay, you need a highly explainable model or you need highly accurate model. Okay, so it's somewhere say that someone says that okay, I need somewhere in between, right? So that trade-off. So we can go with some such kind of algorithm which is bit explainable also, and it will give you a better result than regression model. So for example, decision trees or random forest. So okay, so that's something as a data scientist you have to understand what customer is expecting, and accordingly you have to select the algorithms. So once we go through all the algorithms, we will get even better picture. But so far, guys, did you understand this regression model, or anybody has any questions? Is this clear to everyone? Okay, and now if you have to practice, okay, if you need more data sets to practice, now I'll give you one good source. Okay, just go and say that UCI machine learning repository. Just type UCI machine learning repository. Now, this is a pretty good repository for practicing, okay, machine learning algorithms. So there are 665 data sets available in this particular website. Okay, now you can choose, and here the data sets are from various domain. Okay, so you can just go here, view data sets. Okay, so here you can search through keywords, through data type. You want image or multivariate. Multivariate means multiple variables, right? Or you want sequential, tabular, text, time series, whatever data you want, you can filter from this particular option. And subject area, these are various domains from biology, from business, from climate and environment, computer science, health and medicine, social science. So all these different data sets are available. Now comes the task. Okay, so if you want to uh, run this regression models, okay, where you have to predict the numerical variable, then you can select this regression. Okay, so if you select this regression, so all these data sets are related to regression. If you see here, okay, so you can use this data features also, you can say like less than 10 or 10 to 100. So based on the number of features, you can select the data. And even so, in some of the data sets, there are more than 100 features are also available, right? So if you just go here, okay, so this is again a data set very much similar to the data set what we have used. Okay, so here it is price and all these are different specification of that particular vehicle. So here you can kind of train a model which can predict the price of the vehicle, okay, based on all these different features of the vehicles. You can train that kind of a model. Okay, now you can download the data from here. Okay, if you download it, it will get downloaded in the Excel file, and then you can load it into Python, and then you can experiment or you can try on this particular data. So they have given some information about this data set, and all these data set are close to real data set. It is not something cooked up. Okay, so they will also give you a source of this data. uh, yeah, so this particular data has been published in this particular paper. It is also published in this International Journal of Data Science and Analytics. Okay, so they have given you some reference from where this paper, this data set has been taken. Okay, so in all this paper, this data set has been, there was a citation of this data set. Okay, so pretty good source website, for your practice. There is another website, probably you might have heard about it, Kaggle. Okay, so this Kaggle is a website where it is a platform where competition happens. Okay. So here people will, so here if you see there are different kinds of competitions are happening. Okay. So these are all competition. There is a prize also. There is a uh, prize associated to these competition. And people across the globe, they participate. Even the companies, they participate. Okay, in these particular competitions. So these are all data science and AI competitions. Okay. So here, if you see this, it's close to 1 million, right? Um, so this is the prize amount, which they have put it for this particular competition. Okay, so again, here you will get, these are all real problems. So all these competitions, all these different cases are being put up by companies. Okay, so if you see here, it will give you the overall overview of this, and will also tell you how many people have participated. These many people have participated. These many submissions have happened. Okay. See here if they are saying submission are evaluated using the R2 square, R square score. Okay, so whichever model is giving the highest R square score, that will be those teams will be considered as a winner. Okay, and then they have said how they have to submit and all those things. Okay, so you will get the data here. Okay, so they will explain you. They have split the data also into training and test. So they have given the training data set and the test data set. So you have to train the data on the training and then you have to test it. And then whatever results are coming from the test, then you have to submit it in this particular format. Okay, and then you have to upload it here. So there are many people, they even share their code also. Okay, so go to the code here. So you will find multiple notebooks here. Okay, so people who have participated in this particular competition, sometimes they also share that to their solution to the community, and you can just go here and see how they have solved that particular problem. Okay, so you'll get the entire code here. So this is one of a very good source of information. Here you can get a lot of data also. You just type your domain, manufacturing or life sciences or healthcare, you will get a lot of such competitions happened in that particular domain. Okay, and then you can you can fetch the data, even you can get the solution, you go through the solution, or else you can, if you feel that you can build a better solution, you can go and participate in that competition and then submit it. Okay. All right, so go through it in your leisure. Okay. Look into different competitions if you want the data sets. Okay, so search for the data sets from this particular section. Okay, so there are different kinds of data sets related to various domain, clothing and accessories, economics, NLP related, cancer, health science. So these are all life sciences and healthcare related, COVID type. Okay, so that's how you can go through it. So there is a very good community discussions happening here. So you can go through these also. You will get a lot of understanding. So I would say be an active member in such community so that you will understand what's happening in the market, in the industry, and you will be updated with that. Okay.
Do they
So
give
I'll stop. Yes,
ranking as
sorry.
well in Kaggle? I mean, is there any ranking system also here?
Yes, ranking. So there would be a leaderboard. Okay. Let me go through it. So once the 3 days to go, 13 days. The competition is almost gets over. So a few days before they will put a leaderboard. It's for knowledge. There is a leaderboard here. So this guy is on the top.
Mhm.
Is given no, his score is, I don't know whether it's ascending or descending. Basically, it would be on the top. Okay, this team is on the top. Okay, SZU base for this particular competition.
Okay.
Okay. Yeah, so that's what it is. So I will not pick up the new topic today. So if you want to discuss on anything, let's discuss. Otherwise, give some good time on this linear regression. And if you have any questions, come back tomorrow and ask me. Tomorrow we will pick up a new topic and we will get into some mathematical based algorithms. We will talk about KNN, which is K nearest neighbors. Okay, we'll talk about that particular algorithm. So meanwhile, today. Go through this linear regression, go through these different websites like UCI and Kaggle. There are many more. Okay, if you want to practice, these are the good source of data. Okay, so you can find. So you can just type it here regression. Let's see, what you will get. So simple linear regression. You got one example. Okay, let's click here. So you'll get the entire. So there is a data. So here, people are predicting the salary based on the experience level of the people, right? So this is a simple linear regression problem. So you have a data also, you have the entire code also, you can run this and see how they have done it. Okay. So like that, you type multiple linear regression, you will get some examples around multiple linear regression. So very good. So in our team, we are very active member on this Kaggle. Okay, so we also participate, we also learn a lot of things from other solutions. So this is a very good source of information, guys. Any questions? All right, so if no questions, then we will end this session today. Let's connect tomorrow. Thank you, guys. Have a nice day. Bye-bye.
Thank you.